Good morning. My name is Johnny Danek, and as you know, I'm a technologist primarily specializing in cardiac intervention. Today, I'd like to spend a little time discussing the inflator intervention inflation device, primarily the Monarch digital model. I can't read off these, I'm so sorry. IN2430. It's a handy little gadget designed for the safe metered hydraulic inflation of PTCA balloons and stents. We're going to go over its packaging, features, and deployment. While not part of the actual formal speech, I'll be happy to answer any questions you have. So just as soon as we're done here with the actual reporting part, let me know and we'll continue to talk about it. So starting out, this is the actual device. It's packaged in a sterile, one-time use plastic package. This particular one is the version A, and that means that in the package it comes with the actual device, sterilely packaged, and it comes with a MAP 403 package, which is the MBA. It's got the TUI Borst in there, the metal insertion tool, we also call the wire shaper or cheater, and then a torque device. The torque device, this particular one, is made for 014 wires as opposed to the 035, which is the larger wire, not for intervention use. When delivering it to the sterile field, there's a couple different ways you can do it, and you can either just peel back the package, dump the entire contents to the scrub person, or if you want, you can peel it back and present it, and that gives them the option of taking either just the device, both pieces, or this moves as well. Why do we use an inflator? One of the big reasons is hydraulics. Fluids are not compressible. Pascal, our good friend and hydrodynamic genius, tells us that fluids are not compressible. Realistically, 0.005% when using an oil, over 1,000 pounds per square inch is compressible. In our world, that's not. So basically, for every bit of pressure administered to a fluid, that same amount of pressure comes out of the other end. That's really one of the biggies we use it. The other reason is we administer a contrast and saline mixture through this. It's a half and half mixture. Contrast alone is too viscous, and it won't allow complete collapse of the balloon, so we can't deflate it in a timely fashion. Because it's a mixture of the two, and the reason we need the contrast is that it needs to be visible in the fluoroscopy, which is how we do the procedures. The other reason is if there's a breach in the balloon, the patient simply delivered a small amount of contrast and normal saline, which is what we've been giving them during the procedure anyway. If there were to be a breach and there's air, then it would result in an embolus in the artery, potential harm, even death. We don't want to do that. So let's get to the actual device itself. There's a digital scale. Digital scale has two buttons of operation. There's a green button and a blue button. The green button, push it when you first turn it on, turns on the display, and turns on a little backlight. The blue one actually allows you to toggle between atmospheres and bars of pressure, or atmospheres or bars of pressure and pounds per square inch. Traditionally, atmospheres and barometric pressure is what we normally use. The backlit display has two things, and that's the selected pressure and the time. That actually resets every time we begin to use the device. It's not something we have to keep up with. If you're using an analog device, you can still measure your actual pressures, and that's measured in kilopascals or atmospheres of pressure, but there's no timer, so you would rely on a clock to measure how long your therapy is going on. The length of time that the device is deployed, that would be a balloon or a balloon that's got a stent attached to it, is anywhere from just a few seconds to up to 2.5 minutes. So generally with coronaries, we don't go 2.5 minutes simply because the discomfort to the patient is so great. It It's usually between a few seconds and 30 seconds. But 2.5 minutes for peripheral work is not unusual. The patient, of course, may experience pain or discomfort while inflation is taking place. That's because blood flow is being blocked by the device that's inflated. There is an analog version of this available. We kind of went over that briefly. It essentially works the same way. We'll go over the other features, but instead of a digital display, it's got an analog display. That's the difference between a digital clock and a clock with hands. Some of them also have a greater volume, which allows for larger devices to be blown up. We'll discuss that a little bit more. This particular one has a 20 milliliter capacity. You'll notice the markings. They actually don't start here. They start here, and they go to here, 20 ml. There's a space here, and that allows for the volume difference in the tubing. So as you're loading this and filling it in preparation, that makes that difference. It also allows for air. So any air that's in the system as you're preparing the balloon and stuff can be in this system here as it's inverted and won't go to the patient. Again, you want to keep air from going into the patient. So there's always an airspace that's available to them. There's a driver device that works for this. This is nothing but a big fancy syringe. That's all it is. It works like any other syringe, except instead of just pushing forward on a bolt, it's got a driving mechanism. It's a simple screw feature here, and that allows us to meter. So you can go forward in small increments, you can go back in small increments. You also have a large D handle. That D handle allows you to pull back quickly or to push forward quickly. Back quickly is when you were loading. It's also at the end of a case, also in that moment. When you're going forward, generally speaking, you're not going to directly administer that to the patient. You're going to go forward in small increments while you watch your display. Now, when you pull back, you can pull back quickly, but what's generally used is that we're going to pull back several times to relieve the initial pressure on the inside of the vessel, and then we can pull back, relieving the rest of the pressure on the balloon. And that's the way that's done. Again, this entire thing would be filled with normal saline conjugates. So, my apologies. It's really, from a mechanical point of view, that's all there is to this handy little device. Early interventionalists relied on syringes of varying sizes for their inflation needs. A larger balloon had more volume, therefore they needed a larger syringe. If, however, the lesion that they were working on was a little tougher lesion, they needed to go to a smaller syringe in order to administer greater pressure. Fluid dynamics of syringe volume should be familiar to those of us doing the same. So for those at home, bigger syringes equal less administration pressure, but greater available ability to withdraw from the source. The inverse to that, of course, being true, a small syringe has high pressure out, but does not do so well if one's trying to remove a fluid. The inflator inflation syringe acts like both of those things. So this fairly simple device allows physicians and their staff to administer metered time pressure treatments against blood-occluding plaques within the vessels. Although pretty much you'll find that there's multiple devices, and when we look at these two, they're all going to be essentially the same in basically the way they work. Engineering, health field, it all goes kind of the same, form follows function. You need something to do, a task, they're all going to essentially work the same way.